Hello, I'm going to do the last PowerPoint presentation, unit number 4. And then the unit number 3, you can read and go through it because most of the concepts are pretty clear in that. And in order to do that, I'm going to open the unit number 4, so give you the idea. Basically, the unit number 4, chapter number 12, consists of the phase diagrams. There are two types of phase diagrams. One is the pressure and temperature curve at various temperatures, various pressures and temperatures. And the other one is the phase diagram that we get when we do a phase transition from solid to liquid to gas. And I want to review that because the second item that I talked about, we do it in chapter number 5, thermochemistry, where phase transitions are done pretty much in good strength. And so in that case, when we do the phase transitions from using the physical states of matter, then we have to calculate the total energy for each of the phase transitions that occur. In order to do that, what we do is as follows. So we got to understand what is happening. And therefore, in order to understand what is happening, the following slides will try to explain. First, you have to remember that the phase transition from any one phase to another has a name associated with it, and the energy change required to bring about the change is the same as the reverse reaction that were to come. What do I mean by that is very simple. Melting is the conversion of solid into a liquid. So in order to do such a type of conversion, this is considered as an endothermic reaction. Furthermore, from the thermodynamic point of view, the extent of dispersion of energy from a solid to a liquid is much greater, and therefore it always happens. But it involves the absorption of energy, and therefore delta H is positive because it is an endothermic reaction. The melting point of a solid is the temperature at which the lattice collapses and the solid is converted into a liquid. Like any phase change, melting requires energy, and this particular energy we call it as the enthalpy of fusion. Energy absorbed as heat on melting equals enthalpy of fusion, and it is given as delta fusion H kilojoules per mole. Now, if you want to convert the liquid into a solid, then the energy is evolved, and so it's an exothermic process. So heat on freezing is released because it's an exothermic reaction, and so the enthalpy of crystallization has the same value, numerical value, as the enthalpy of fusion, but a negative sign. And there are many other phases that you are supposed to know. So the phase changes involving solids. Enthalpy of fusion can range from just a few thousand joules per mole to many thousands of kilojoules per mole. And here, in this, various different compounds and elements are shown, and their melting points are shown, the changes of the ions are shown, and you can see how which force comes into play. Because remember, the energy and the melting point or boiling point is a function of the intermolecular forces. And so if you forgot the intermolecular forces, then go back and read the chapter 11, and I would suggest you better read the chapter 8 also, because it deals with molecular geometry, electron pair geometry, molecular geometry, and gives you the definitions of or the identification for the polar molecule, non-polar molecule, and how you can quickly identify whether a molecule is polar or not, and the bond angles associated with it. Now, the next phase change is phase change involving solids. Sublimation is conversion of the solid into a vapor state without going directly through the liquid state. So the solid gas energy required as heat. So you get sublimation, like fusion and evaporation is an endothermic process. The energy required is called as the enthalpy of sublimation. And so this is a repeat slide, so let's delete the first slide. And so now you have it correct order. And so now the transition between the phase diagrams. The phase diagrams are used to illustrate the relationship between phases of matter and the pressure and temperature that you have. When, for any phase diagram that you get, let's go back. For any phase diagram that you do, you must remember that all the three phases must be shown. And it doesn't matter if only three phases are shown, but you can show different allotropic forms, etc. But it all must be on the same PNT curve. That is it. Now, you have to understand what each of these points and lines mean in terms of equilibrium state and the state of the material and what changes are taking place. In order to do that, we can see that for this is a phase transition for water. And so what we see is that we have a solid phase, a liquid phase, and a vapor phase. Now, right when the temperature is equal to the boiling point, then you must always remember that the normal pressure, atmospheric pressure, will be 1 atmosphere. So normal boiling point is defined as the boiling point at which a liquid changes from a liquid state to a vapor state under 1 atmospheric pressure. Now, if the pressure is lower, then remember boiling point lower, because that gives rise to the Gay-Lussac's law. Pressure is directly proportional to temperature when the volume and the amount of gas is kept constant. And so you have to remember that. And the same definition goes for freezing point. The freezing point occurs at a temperature at 1 atmosphere pressure. And so now let's describe each of these. First, the lines. So we have described the blocks. So you have 3 blocks, solid, liquid, gas or the vapor state. Then we look at each of the lines. The line BA, shown at the bottom, gives you an equilibrium between the gas phase and the solid phase. Between A and C, it represents an equilibrium between the liquid state and the vapor state. And the line between A and C represents the equilibrium between the solid state and the liquid state. And in the case of water, you see that the slope of the line is negative. And therefore, we find that as the temperature is lowered, we can compress the water molecule and it will turn to a liquid. And so water has the highest density at 4 degrees, but 4 degrees Celsius, but we see that, so any substance, any part of water which lies on A and B is neither a solid nor a vapor. It is just an inequilibrium between the two phases. If it falls, if suppose we have a particle labeled as X, and if it is in the solid part, like the point A, right on the top, then it is completely in the solid phase. That means it is frozen or ice. But when it comes to B, it is not. It is like in between solid and liquid, but the phases are in equilibrium. If the temperature rises a little bit, it will go into the liquid state. If the temperature falls very, very slightly, then it would go into the gas phase, the solid phase. And same thing between the point C, where if C is on the equilibrium line. So at this temperature, it is neither a solid, it's neither a solid or a liquid. Depending upon the temperature, it can go into any phase that is there. If the temperature rises, it will go into the vapor state. If the temperature falls, it will go into the liquid state. And there you can clearly see the normal freezing and boiling point, melting points of the material that is there. Now, the question is, how do we define the point A? Because AB is one equilibrium line, AC is another equilibrium line, AD is another equilibrium. A is called as the triple point because all three equilibrium phases meet at the point A, and that is called as the triple point. So in the case of water, the triple point is 0.01 degrees Celsius and 4.58 millimeters of mercury. So from the phase diagrams for water, we see that water has a maximum density at 4 degrees Celsius in the liquid phase. Most substances have a maximum density in the solid phase. Hydrogen bonding accounts for water's deviation from normal behavior. At constant temperature, an increase in pressure can bring about a phase change from solid to liquid. At constant temperature, an increase in pressure, that's the same statement repeated twice. So just to make sure that you remember it, but I'm going to delete that line. And we say at constant temperature, an increase in pressure can bring about a phase change from solid to liquid. And this occurs naturally if you're a very good ice skater, because this occurs when the blade of an ice skate runs on the ice. Ice skaters usually ride on a thin film of water, not the ice. So now this is another phase diagram, and we can see that some of the points have been cut because the points are so far off and they've just joined it after 16 atmospheres and then broken the curve and then continued on. And we can do that in graphs if you are plotting, but you have to give an explanation. That is it. So the temperature is from minus 100 to plus 60. And then and the pressure is from zero atmospheres to very high, because beyond 16, 16, it is not showing. So you know that it's under high pressure state. Now, in this particular graph, you will see some of the most important items that you learned in your chapter number 11, especially when it comes to the liquid state. First of all, we see that if you look at the carbon dioxide, it has a forward slope of the solid-liquid boundary. The solid and the liquid boundary, we see that the straight line from the triple point is falling towards the right and not towards the left. This is seen because carbon dioxide does not show any hydrogen bonding, and so it has a positive slope. Next, we see that the triple point for carbon dioxide falls at minus 56.6 degrees Celsius, and the pressure at that temperature is 5.19 atmospheres. Secondly, we see that around 31 degrees Celsius, which is almost room temperature or slightly above room temperature, the critical carbon dioxide has the critical temperature, and the critical pressure at that temperature when carbon dioxide gas turns to a supercritical fluid is 73 atmospheres. and therefore we see that we can get from the plot, a triple point phase diagram. It is possible to evaluate the critical point, the critical temperature, pressure, supercritical fluidity state, and all the phases in between can be described by the phase diagram. Many times when they are making alloys and different compounds from mixing elements, then phase diagram is very, very important to study the phase diagram, draw the phase diagram to find out where exactly you will get a good mixture. And a mixture, when we say a good mixture, that means the whole melt will be homogeneous, and the temperature at which that occurs is called as the eutectic point. So below is a phase diagram for oxygen with the scale greatly exaggerated. What do we call the point P? 2 mmHg and 54.34 Kelvin. That point, because we see that there are three phases interacting, we call that as the triple point. So you can logically define. Use the phase diagram for carbon dioxide below to answer the question. Go ahead and do that. And with that, I finish the phase diagram for you. And I'm going to stop the share, and we are done with the